So now we are on to reaction mechanisms. So we're going to start with 14.5 and then go back to 14.4. So a mechanism is a series of elementary steps that combine to show the path molecules take from reactants to products in a chemical reaction. So up until now you've just seen an overall balanced reaction, but you haven't seen how two molecules collide to form something, and those then collide with another thing to form something else, and there's a series of steps that take place to get to the overall complete reaction. An elementary step is a reaction that represents a single collision in a reaction mechanism, and its rate law can be written from its reactant coefficients. This is not what you've learned before. In the overall reaction, we cannot use the reactant coefficients, but when we have a mechanism, we actually use the reactant coefficients as the power for, or the order, the exponent, for each chemical. We'll do some examples of this. A unimolecular step is a step in a mechanism that has only one reactant particle. We have bimolecular steps and termolecular steps. Bi 2 particles, ter 3 particles. Most common is uni or bimolecular steps. Termolecular steps, you need 3 particles to combine together all at the same time, and that's not very likely. Much more likely is 2 particles colliding, or not having to have any collisions at all. Okay, some rules for mechanisms. You should have these written down already. Okay, so the steps have to add up to the overall reaction, and these might not seem to make any sense, but they will once we put this into action. The rate determining step, or the slow step, you're always told which step is slow, or you're given information to figure it out. The slow step gives you the rate law for the overall reaction, where x and y are the coefficients. That's this little part up here that I was just talking about. The rate law of an elementary step can be written from its reactant coefficients for any step. The actual rate law for the overall reaction is based on the slow step. Okay, and this goes against what we learned earlier. We cannot use the coefficients from the overall balanced reaction, but we can use the coefficients from the slow step of the mechanism. Okay, some definitions. Intermediates. These are things that appear as a product in the mechanism and are later, in a later step, used as a reactant. They're not allowed to appear in the rate law, so if they do, we have to do something to get rid of them. Now, catalysts, we've learned, make reactions go faster. They can appear in the rate laws, and the way you know the difference between a catalyst and an intermediate, catalyst versus an intermediate, the catalyst first appears as a reactant in the mechanism, and in a later step, or in the same step, it appears as a product. But the first time you see it, it has to be seen as a reactant, and then it can be in a product. Catalysts are not in the overall balanced reaction. All right, let's do an example. So, we have a reaction and a proposed mechanism. So we have 2 steps. In the first step, an NO2 and an NO2, 2 of these, come together. And that step, you're told, is slow. That's just a proposed mechanism. And then one of these intermediates, notice this was produced and then used. This intermediate combines with a carbon monoxide molecule, and then we produce another NO2 and a CO2. So if we add these 2 together, we get the overall balanced reaction. And we're going to check, is this mechanism consistent with the reaction? Well, the mechanism has to add up to the overall balanced reaction, so let's check that. When we add those 2 pieces together, what do we get? We get the balanced reaction. Because an NO2 cancels out with an NO2, and an NO3 cancels out with an NO3. Now this NO2 is not an intermediate or a catalyst. It was a reactant, so it's just a reactant particle that gets used up and later produced, but it is in the overall reaction, so it's not a catalyst or an intermediate. Now, as for catalysts or intermediates present, let's see. This right here gets produced and then used. Therefore, NO3 is an intermediate. This is another view of that reaction we were just looking at. So step 1, step 2. I took all these chemicals and just giving you a pictorial representation. Step 1, NO2 and an NO2 come together to make an NO3 and an NO. And then this NO3 combines, it's right here in step 2, combines with the carbon monoxide to form another NO2 and a CO2. The NO2s cancel out, one of them does, the little Mickey Mouses, and the NO3s cancel out, and we get our overall balanced reaction. So we have found that this mechanism is consistent with the overall balanced reaction. Now we want to see if it's consistent with the rate law. So we find experimentally that the rate law for this reaction, this is usually given to you, or you're asked to determine it based on a mechanism. But we're told this is the reaction rate law, the rate law for the reaction. And now we have to find out, is this mechanism consistent with that? Well, we were told this is the slow step. Okay, so here's our slow step. And we are also told that the rate law is based on the coefficients of the reactants in the slow step. That was this piece of information right here. The rate is K, A to the X, B to the Y, where X and Y are the coefficients for A and B in the slow step. So here we are. Here's our slow step. These are our only reactants in the slow step, so it will be NO2 times NO2, which is NO2 squared. So looks like we were consistent with the rate law, because the slow step was step 1, based on that rule 2 in the mechanism. The rate would be K times NO2, which is NO2 squared, and it matches. And that means that this mechanism, the proposed mechanism, is consistent. It does not mean it is proven to be. Okay, so the mechanism is consistent with the rate law. It's consistent, but there's an important note. We can't prove a mechanism absolutely. We can show that certain mechanisms cannot be true. We can eliminate ones if they don't satisfy the rate law, but we can't prove a mechanism is actually the correct. Okay, we're going to do another problem. So we have a reaction. And the reaction is given right here. And we want to know which mechanism is consistent with this rate law right here. So let's check. The first mechanism, the slow step, we base the rate on the slow step. So the rate would be K times ClO1 minus times ClO1 minus times ClO1 minus, or ClO1 minus cubed. That does not match the experimental rate law, so we know that this mechanism doesn't work. Can't be that one. Now the other one, let's see. Based on this mechanism, mechanism B, first step is slow, so our rate would be rate is K times ClO1 minus ClO1 minus. So we'd get K ClO1 minus squared. And that does match the experimental rate law. So that tells us that mechanism B is consistent with the rate law. It doesn't mean it's the exact mechanism, but it is a consistent mechanism. This matches the experimental rate law, so the mechanism might be correct. Okay, now we want to know, is the proposed mechanism consistent with the overall reaction, and determine if there are any catalysts or intermediates. So to be consistent with the overall reaction, the mechanism has to, the steps in the mechanism must add up to the overall reaction. So let's see, can we cancel anything out? The ClO2 cancels. Again, you can pause and do this on your own if you would like. That's all that cancels. So we end up with 3 ClO1 minuses, making a ClO3 1 minus and 2 Cl1 minus. And that was the original reaction that we were given right here. So that part's consistent. And now intermediates. Well, right here. ClO2 1 minus is produced and then later used. That's an intermediate. I don't see any catalysts. Okay, this one's a little tricky. Well, you're not going to be able to do it on your own, so you want to pay attention here. So this time we go to the slow step, and the slow steps gives us this rate. I've got this little K1F. That's the rate constant for the forward reaction, step 1. K1R, rate constant for the reverse reaction. All of a sudden we've got this reversible reaction. You'll learn what that means shortly. And then I have K2 forward, which is step 2, the rate constant for the forward reaction. So the rate for this would be K2F times O times O3. That's what we've learned. Looks okay. Ah, we got a problem. O is an intermediate. It's not in the overall reaction. It appears here, is later used up. We can't have intermediates in our mechanisms. Let's look, where's that rule? Intermediates are not allowed to appear in the rate law. We cannot have that intermediate. We got to do something to get rid of it. So now you'll learn how to do something to get rid of an intermediate. We actually use this fast reversible step right here. So what does that mean, fast reversible? It means the rate forward is equal to the rate reverse. And we know that rates can be written as the rate constant times the concentrations. So the forward rate, let's look at this. What is that forward rate? Let's look back at the reaction so you can see it. The forward rate would be the K1 forward times the O3 right here. The reverse rate would be K1 reverse, step 1, rate constant for the reverse reaction, times O2 times O, right there. Okay, we now have an equation where we can isolate O, the concentration of O, and then plug that isolated O back into the original rate, substitute that right in here, and we'll have a new rate without any intermediates. So wrote that down, isolate the concentration of O, plug into the rate law from step 1. So first I'm isolating O. All I did was move this equation around to isolate O. I'm going to plug this right in here. And the result is this right here. That looks really ugly. And if I have a constant times a constant over another constant, that's just a constant. And I can call that K prime. Whenever you have a whole bunch of constants, we just call them K prime. And we rewrite our rate. Makes it a little bit prettier. You could leave your answer like this, but notice we have O3 squared over O2. Okay, new problem. So this is the proposed mechanism for decomposing phosgene, which is a really dangerous chemical, but this is the proposed mechanism. It's believed the first step is fast equilibrium. EQ means fast equilibrium, which means the rate forward equals the rate reverse, then a slow step, then a fast step. And based on this mechanism, what is the rate law? One quick thing, we never use a fast equilibrium that occurs after a slow step. That will not help us. We have to use the fast equilibrium step that is above a slow step. So you start with your slow step. We'll find that there's an intermediate in here, this Cl we have to get rid of. We will use the fast equilibrium up here, just like in the last problem. Isolate the Cl, plug it into this rate law, and solve. So pause if you want to do this on your own. Here we go. So the rate is just K2 forward. And again, these constants don't matter so much. I'm just trying to show you how it really is, and then we simplify. So it's K2F times phosgene concentration times the Cl concentration. And based on our forward rate equaling our reverse rate, because of the fast equilibrium, notice the arrows back and forth in fast equilibrium, we can write that K1 forward times Cl2 is K1 reverse times Cl squared, right there. We're going to isolate Cl. That's what we get when we isolate chlorine. And then we're going to plug this, substitute that value for chlorine, substitute this whole thing into the chlorine right there. Whoop! We are going to stick it in right there. And we obtain this ugly looking equation, which you could leave as is, or we can recognize here's a whole bunch of constants, doesn't matter what they are. We can just call those K prime and rewrite this as K prime concentration of phosgene times the concentration of Cl2 square root. This one's easy. You should be able to do it on your own. I'm about to show you the answers. So pause. That was a really straightforward one. Nothing tricky, no intermediates in the rate law. Okay, now we'll go through section 14.4 after 14.5. Activation energy and temperature dependence on rate constants. We talked about this in class a little bit. Collision theory. First you need to know the collision theory. Particles have to collide in order to react. They have to be in the correct orientation when they collide. And they have to have enough energy to overcome the activation energy needed to react. What is this activation energy stuff? It's the difference in energy between the reactants and the highest point on an energy diagram. What is an energy diagram? This is an energy diagram. Okay. The activation energy, that's that threshold energy. You need at least this much energy to get over the hump, and once you have that much energy, the reaction just goes forward. You got this much energy, boom, the reaction happens. We produce products. That's the threshold amount. We need at least that much. So we start with a reactant amount of energy. We have to have this much energy to get over and produce products. Okay, this is just a model right here of the chemicals right here. This is two BRNOs. This is the NOBR, BR, and O, and then here are our products, two NOs and a BR2. This right here is called the transition state or the activated complex. Those are important vocabulary words. You need to know that. Both the words activated complex and transition state. So now, order of a reaction. What does it represent? It represents how many particles are in the transition or activated complex, transition state or activated complex. Now that's an oversimplification because sometimes we have these fast equilibrium steps, so sometimes it's a bit more complicated, but basically the rate law, the order of the reaction, those exponents on the rate law, are telling you what is in the activated complex or the transition state for the slow step, assuming we don't have a goofy equilibrium step. Okay, the bigger EA is, the slower the reaction is, because fewer molecules have enough energy to overcome the activation energy. So the higher the hump, the slower the reaction. That is a very important concept that you need to know. Got to know that. Okay, last thing, how do we find activation energy? We have this equation right here. We're not going to do any problems with this. There's something called the Arrhenius equation. If we know the activation energy, we can find the rate constant for a reaction at any temperature. Well, we also have to know this thing called A, the Arrhenius constant. So this K is the rate constant, EA is the activation energy, T is temperature, of course in Kelvin. Now, in order to find the activation energy, you can always do a plot of ln of K. If you find K at 2 different temperatures, or 3 or 4 different temperatures, you plot ln of K versus 1 over time, and the slope is negative EA over R. So you multiply the slope by 8.314 joules per mole Kelvin, and you'd get the activation energy. We're not going to do those problems, but it's just background information. The important thing is, K depends only on temperature. I'm not crossing that out, I'm trying to underline it. So your rate constant depends only on temperature. Very important thing to know. That's a star, that's an asterisk. Okay, we're almost at the end here. Energy diagrams, sometimes you will see, I can speak, an energy diagram showing each step of the mechanism. So right here, this would be a 1, 2, 3-step mechanism, and it's showing you the energy of the original reactants, and then different transition states, different products that are being made, and then the 3rd step, and down to the final product for this reaction right here. The highest hump, the largest hump, is the slow step. And the activation energy would be the distance from the reactants all the way to the top of the hump. That's your activation energy, reactants to the top of the highest hump. And the largest hump is the rate determining step. All right, last section, catalysts. These are really easy. Okay, catalysts lower the activation energy. So here's an energy diagram. Here's an uncatalyzed reaction. Here's the catalyzed reaction. Notice the activation energy is lowered down. And here we go. How does that work? Catalysts lower the activation energy by providing an alternative mechanism for the reaction. And reactions go faster because more of the collisions are effective. And that is it.